Aloha, everyone. Let's go ahead and get started. So I'd like to welcome you all here and thank you for attending our monthly College of Natural Sciences webinar. My name is Allison Sherwood. I'm the Interim Associate Dean for the college. And through our Pilina webinar series, we're aiming to reach the broader community and share the world-class research that happens both in the College of Natural Sciences and also across the Manoa campus. Today's presentation features Dr. Rob Jedicke, who's a professor at the Institute of Astronomy at the University of Hawaii at Manoa. Dr. Jedicke has had a professional career in particle physics, in astronomy, and also in software engineering. He received his doctoral degree in experimental particle physics from the University of Toronto in Canada. After a brief tryout with the BC Lions professional Canadian football team in Vancouver, he held postdoctoral positions at the Fermi National Accelerator Laboratory in Batavia, Illinois, and at the University of Arizona's Lunar and Planetary Laboratory, where he worked on the Spacewatch Near-Earth Asteroid Survey. He spent more than 5 years at Vico Corporation in Tucson, Arizona, developing image analysis software for interferometers before accepting a faculty position at the University of Hawaii's Institute for Astronomy. He was the development manager of their moving object processing system for the Pan-STARRS telescope on Maui that is now the world's leading discovery system for asteroids and comets. His current research includes working with Astronautica Corporation to develop techniques for mining asteroids to provide water as fuel for spacecraft missions. And so now I'd like to turn our time over to Rob for his presentation, Einstein versus Santa. Is Santa breaking the laws of relativity? Welcome, Dr. Jedicke.
Thank you, Allison. Yeah, I don't know if this is world-class research, but I think it's an extremely important question to be talking about at this time of year. The question is whether or not Santa Claus is guilty of breaking the rules of relativity as defined by Einstein. So I think it's a really important question. And just give me a second here. I'm going to put on my hat because I can see some of you smiling. I think that's because you think this means that I'm somehow prejudiced or biased towards Santa Claus. And I want to share that that's not the case at all. I am a hardcore scientist. I am only influenced by facts and data and evidence. I'm not prejudiced in any way towards or against Santa Claus. This is just going to be purely a scientific talk. So the first thing I did, of course, if you hadn't asked the question, is Santa Claus real, is I did what everybody does nowadays. I went online and I asked the question, is Santa real? And there's this great website called Ask 500 People that you can ask any question you want, and it'll get you answers from all sorts of people all over the world. So I asked the question, is Santa Claus real? And came back that about 42% of the respondents responded that Santa Claus was indeed real. But I think that, and it gives you all sorts of great answers, as a function of what country they come from. But I think that it's much more interesting to sort of break it down into sort of like a larger statistics. So I looked, for instance, at the fraction of people in both the United States and Canada that think that Santa Claus is real. In Canada, 43% of the respondents said that Santa Claus is real, whereas in the United States, only 28% said that Santa Claus is real. Now, you might think that's kind of interesting. I think it's actually not surprising at all, because in Canada, our national police force, the Royal Canadian Mounted Police, looks a lot like Santa Claus. In fact, I think you could argue that the RCMP outfits are designed or based on Santa Claus's outfit, right? And, I think that is no surprise that the people in the United States are less likely to believe in Santa Claus because your federal police force looks like this. Right, so big difference, and I think that explains why Canadians are more likely to believe in Santa Claus. There's another way to look at it is by country, by religion, whether or not they voted, whether they think that Santa Claus is real or not. So it turns out that in Christian countries, only 38% of the respondents thought that Santa Claus is real, whereas in other countries, countries that are not Christian, 61%, that's 50% more people voted for Santa Claus being real. So I think this is really interesting, and I think it has it'll come into play later when we have to decide how far Santa Claus actually needs to travel in order to deliver all the gifts around the world. Because if he has to deliver gifts to every person in the world around all the different countries, it's a much more difficult problem than just delivering gifts to just the Christian countries. So let's talk about the origins of Santa Claus. Santa Claus is thought to be, or rather inspired by the Christian figure or the Christian Saint Nicholas of Myra. Saint Nicholas was a bishop in the province of Myra, which is now in Turkey. And he's famous for his generous gifts to the poor, in particular for presenting gifts to 3 impoverished daughters of a pious Christian so that they would not have to become prostitutes. So he's now known as a patron saint of children, a patron saint of lawyers, and also a patron saint of prostitutes. So the modern origins of Santa can be traced back to 1823. That's about 200 years ago, with the poem that "'Twas the Night Before Christmas." And I think a lot of us have ideas about what Santa Claus does and how he acts based on that particular poem. But the first actual image of Santa Claus didn't appear until 1863 and on the cover of Harper's Weekly. So that's like 160 years ago. This image here that you can see, this person right here, is the first drawn image of Santa Claus. But I think that most of us actually have a picture of Santa Claus that's formed more by Coca-Cola over the past century than by any actual photographs of Santa Claus that have been taken. What about the origins of Einstein? Einstein was born in 1879 in southern Germany, about 140 years ago. His parents were Hermann and Pauline. One myth about Einstein was that he did not have a lot of education or formal training. That is actually incorrect. Einstein did have a PhD, and he was taught mathematics and physics, both formally and informally, at a very young age. He was using calculus when he was only 12 years old. And for Einstein's discoveries, he was named Person of the Century. You know how Time magazine lists a Person of the Year every year, but Einstein was actually, they decided to call Einstein the Person of the Century. And I think that's really incredible when you think about how many important people lived during that entire century, that Time magazine chose a scientist over a politician or maybe a football coach. I mean, that's really an impressive statement that Einstein had such an impact on our world that he could be named Person of the Century. Einstein was named Person of the Century for his various scientific discoveries. He probably should have won at least 3 Nobel Prizes, but he actually just won 1 in 1921. His Nobel Prize was not for relativity, as most people would think, but for something called the photoelectric effect, which I will not be talking about. But he wrote, and he also defined the theories of relativity, special theory of relativity, and the general theory of relativity in papers that he wrote in 1905 and 1915 specifically. So what we're going to do is we're going to use the scientific method to try and decide whether or not Santa Claus could be real, or whether or not Santa Claus is actually breaking the laws of relativity. And I think I need to explain a little bit in the beginning of what exactly the scientific method is. So Poincaré said that science is built of facts as a house is built of stones. But he continued that, but an accumulation of facts is no more science than a heap of stones is a house. So just accumulating facts is not science. Science is about describing the facts and how they operate together mathematically, and so that we have a deeper understanding of how everything works. And I'd like to illustrate this with a typical way that people talk about scientists, as if scientific belief in something is the same as a belief in anything else. So they often say something like, scientist X believes in the theory Y. And when they say that, they often put this emphasis on believes. As scientist X believes in the theory, and they put theory in air quotes, right? So scientist X believes in the theory Y, right? And so it might be, to make it specific, they might say, Dr. Robert Jedicke believes in the theory of relativity, as if that's equivalent to, believing in anything else. But I think, even if I might say something like that, it's really just a short form for what I actually mean, which is Dr. Robert Jedicke accepts the mathematical framework developed by Einstein and known as the theory of relativity as the current best explanation of the observed effects of gravity and relative motion until it is proven wrong. And I think that's the key fact in the scientific method, until it is proven wrong. Those 5 words are what really differentiates the scientific method from anything else. There are no final truths in science. The scientific method only proves theories wrong. It can never prove that a theory is right. So what we're going to be trying to do is we're going to try and prove, we're going to see whether or not we can prove that that Santa Claus is not real using the laws of relativity. So we start off with an observation or a fact. We know that gifts appear under the Christmas tree the morning of December 25th every year. Okay, that's an observation. We all know that that happens, right? The hypothesis is that the gifts are delivered by on the night of December 24th by a large man wearing a red suit driving a sleigh powered by 8 reindeer. Okay, so that's the hypothesis or the theory that we're trying to test with the scientific method. So we're going to test it against the theory of relativity. And so why would we test Santa Claus, the hypothesis of Santa Claus against the theory of relativity? Well, the theory of relativity is extremely well-established explanation of how the universe works. It was developed or stated by Einstein in early 1900s. It's been around for over 100 years. And for 100 years, scientists have been trying to
join the meeting.
Scientists have been trying to prove it wrong. And why are we trying to prove it wrong? Because the first person or the first group that proves the theory of relativity wrong is going to win a Nobel Prize. So it has stood the test of time over more than 100 years, and it is proven itself correct to very high accuracy, very high precision. So if we could show that Santa Claus is breaking the rules of relativity, that would mean that Santa Claus could not exist. So what is relativity? I'm not going to go into a lot of detail about it. I'm certainly not going to get into the mathematical details, but relativity is a mathematical theory that describes how time, speed, mass, all are affected by how fast you're moving and how strong the gravity well that you're located in is. So the faster you're moving, or the more intense gravity well that you're in, the higher gravity that you're actually feeling, actually affects the passage of time. It affects your measurement of speed, and it affects your measurements of mass. So I might talk about a relativistic Santa, and many people would talk about the word, they would say something is relativistic. Well, what does relativistic mean? Relativistic just means that the thing that is
join the meeting
is moving at a speed that is a significant fraction of the speed of light. So if you're moving at 90% of the speed of light, that means that you're moving relativistically or at a relativistic speed. Also, if you're near very, very close to, say, a black hole is very, very strong gravity. And so when you're close to that very strong gravity, you're also going to be experiencing the effects of relativity. So let's talk about the origins of the theory of relativity. We've talked about the origins of Santa Claus, the origins of Einstein. Let's talk about the origins of the theory of relativity. Well, I think it all goes back to understanding waves. In Hawaii here, we're very familiar with the concept of ocean waves. Ocean waves transmit energy over a long distance. And so basically an ocean wave requires water to transmit energy. Right? In the same way, sound waves travel through air. If there was no air around us, we could not hear any sound. Sound waves require air in order to travel, or some kind of other solid medium. So sound waves require air, ocean waves require water, and even there are waves through the earth. There's seismic waves caused by tectonic plates that are grinding against one another. When they lurch against one another, they create these waves that actually occur through the surface of the earth, through the ground, right? There's actually waves, and this is a simulation here of waves that occurred during an earthquake in Italy, passing actually through the surface of the earth. So all those 3 different kinds of waves have 3 different kinds of media. But what about light? What kind of media does light require in order to travel? Light seems to be able to travel through air. Light seems to be able to travel through water. If you're underwater and you open your eyes, you can still see things. Light can travel through glass, right? We know we can have glass windows and light still travels through it, right? So light seems to be able to travel through lots of different media, but what is absolutely necessary for light to travel through? So let's go back to what light actually is. Sometimes you can think about light being a wave, other times you can think about it as a particle. In this particular slide, we're going to consider light as a wave. So if you take white light from the sun, and you were to pass it through a prism, you would get a spectrum of colors, just like a rainbow. And the spectrum is really nothing more than different wavelengths of light. Long wavelengths of light correspond to red light. Short wavelengths of light correspond to purple or red or blue light. So you can think of what a wavelength is the distance between the peaks of these waves, right? So this is the wavelength here. So things that have waves that have a long, big separation are basically red light. Things that have a small separation are blue light or purple light. And when you look at a rainbow, one of our beautiful rainbows that we see so commonly here in Hawaii, and you see the red light, the red end of the red edge of the rainbow, that's because the light coming from that red edge has got a longer wavelength than the light coming from the blue edge of the rainbow, which is a shorter wavelength. Right? So different colors are due to different wavelengths or frequencies of light. Now this comes into play as I try and explain the origins of the theory of relativity. Because think about space now. Think about light in space. We know that the sun emits light, the earth receives it, but between the sun and the earth, there's a vacuum. And this has been known for a long time. It was known back when special relativity was first postulated by Einstein in the early 1900s. So there's a vacuum in space, but somehow light gets from the sun to the earth. And at that time, over 100 years ago, it was very difficult for the scientists back then to understand how could light do that. Every wave that they knew of at that time had to have some kind of a medium that it needed to pass through. So what the scientists did is they proposed there was something they called the luminiferous ether that was permeated all through space. And that was the material through which light could actually travel, right, through a vacuum. So that there really was no vacuum in space. There was this luminiferous ether through space. And that allowed light to travel. But this luminiferous ether had to have very special properties. It had to have a property that it was a massless fluid without viscosity. So viscosity is a measure of how easily a liquid flows, right? So you've got this liquid that's massless, which seems kind of crazy in the first place, and it can flow without viscosity, which means it has basically sort of no friction at all. It just flows very, very smoothly. It had to be perfectly smoothly distributed throughout space. There couldn't be any lumps of it anywhere. And it had to be millions of times more rigid than steel. Right? Now, this all just seems absolutely impossible to believe, but this is in fact the properties that the luminous ether had to have in order to support the passage of light moving at light speed. So before I go on, I'm going to describe a little bit, I'm going to give you a very quick lesson in relative motion. So imagine that you've got a pitcher and a catcher that are just throwing a ball back and forth. The pitcher can throw a ball at, say, 150 kilometers per hour, and ignoring the effects of air resistance, that ball is going to hit the pitcher's mitt at 150 kilometers per hour. That's a very simple problem, right? Now imagine this kind of a scenario. Imagine that the catcher is now sitting on top of a fast sports car. And the catcher is now sitting on top of the sports car. And the pitcher pitches the ball, the sports car is moving at 100 kilometers per hour. And the pitcher still can throw at 150 kilometers per hour. So now in your head, very quickly, do the calculation on how fast that ball is going to hit the pitcher's mitt, the catcher's mitt. It's going to hit the catcher's mitt at 250 kilometers per hour, of course. Well, what about this scenario, where now the car is moving at 100 kilometers per hour to the left. The pitcher is still pitching at 150 kilometers per hour. Now, how fast is the ball going to hit the catcher's mitt? It's going to hit at 50 kilometers per hour. Okay. So now what does this all have to do with the speed of light? Imagine this scenario. So now we've got the luminous ether here. And imagine we have a star, a very, very distant star that's emitting light at some specific wavelength coming at us, right? So the wavelength of light here is represented here. The star is a very, very distant location to the upper left. Now we know that the Earth moves around the sun. So the Earth at this location here is moving downwards and to the right, which means that it's moving away from the star. So that means that using the same analogy of the pitcher and the catcher, that the light that we receive from the star would be moving slower, right? We're moving away from the star, and therefore the light that we receive from that star should be moving slower in that location, right? On the other hand, in this location here, the Earth is moving towards the star, right? So in this particular scenario, the speed of the light from the star and the speed of the Earth in its orbit should combine to make the speed of light look faster, and therefore the wavelength of the light that we should be detecting from it should look smaller, right? And finally, in this orientation here, when the Earth is moving perpendicular to the direction of the star, there's no direction of the Earth towards or away from the star. So that means that there should be really no change in the speed of light that we measure coming from the star, right? So if we measure the wavelength of light in these three different orientations, we should be able to tell whether or not the speed of light is changing. So in the early 1900s, these scientists developed this experiment, which I think is really incredible. They did this without computers. They did this without lasers. They did this without, GPS and fancy, cameras digital cameras like we have nowadays. It's absolutely incredible that they could do this experiment. And I'm not going to go into a lot of details about it. I'll point out that it is all the equipment is mounted on this granite block here, and the granite block floats on a big pool of mercury. That'd be really hard to do nowadays to get it just past the safety requirements. So it's floating on this big pool of mercury, but the purpose of this piece of equipment is actually just to measure the speed of light. And what it can do is it can measure the speed of light along that axis and along that axis, right? And so what they would do is they would align, say, one of these axes with the direction of the Earth's motion, and they would measure the speed of light in both directions. And then they would rotate the equipment around, or they would wait for the Earth to go around in its orbit, and they would measure the speed of light along this other axis. And they could basically try to see whether or not there was a difference in the measured speed of light in these different directions. Well, this experiment is known as the Michelson-Morley experiment after the two scientists who developed it. It's also known as the greatest experiment that ever failed. This experiment basically failed. Michelson and Morley set out to show that the speed of light was different in different directions. And what they found was that there was no difference in the speed of light. No matter which direction they moved it in, the speed of light never changed, right? Now that's really incredible, right? We know that, with the pitcher, the catcher and pitcher analogy, that speeds of things that are, the relative speeds between two objects should change depending on their relative speeds. So this really perplexed scientists for a long period of time. And, they came up with ever more complicated explanations to try and understand why it would happen. But it was the brilliance of Einstein. Einstein was the one person who actually came out and said, well, no, the experiment is probably right. And let's assume that the experiment is right and see what that means. What he assumed then was that there's a universal speed limit, the speed of light, and it's about 1 billion kilometers per hour. I like that number because it's an easy number to remember, 1 billion kilometers per hour. So this speed limit, the speed of light, is the same regardless of how fast you're moving, right? Or how fast the thing is moving towards you, right? The speed of light is always constant. And it seems completely contrary to our conventional wisdom, but it is in fact the way the universe seems to work. So let's talk a little bit about how fast this is, because 1 billion kilometers per hour is really, really fast. How big is 1 billion? If you were to count to 1 billion, saying one number every second, it would take you about 30 years to get to 1 billion. But let's ask a guy who's probably got $1 billion that he can loan us, okay? And we're going to ask him for 1 billion $1 bills. Right? And let's try and illustrate. We all know how big a dollar bill is. We all know how thin a dollar bill is, right? So if you were to take a $1 bill, actually $1 billion bills, and if you were to line them up along the equator, edge to edge, $1 billion bills would go around the Earth's equator 4 times. Another way to think about it is if you took a stack of $1 billion and you just stacked them on top of one another, that stack would be 100 kilometers high, 60 miles high. And to put that in perspective, Mount Everest is 10 kilometers or 6 miles high. And the space station orbits the Earth 350 kilometers above the surface, right? So a stack of $1 billion bills is very, very high, even compared to the altitude of the space station. So many people wonder, relativity, why? Why is there this universal speed limit? Why does it appear that the speed of light is constant no matter how fast you or the thing that's moving is moving towards you? It's just because nothing can travel faster than the speed of light. And then people say, well, why can't anything move faster than the speed of light? And well, that's just the way the universe works, right? But the way that the universe works, and this one assumption has got tremendous implications for how we observe the universe and what we see happen. So now we're going to use the fact that the theory of relativity is a well-established theory that's been tested for over 100 years and never been shown to be wrong. And we're going to test the theory of Santa Claus against the theory of relativity. So we're going to start off for our first test. And our first test is, does Santa Claus have to travel faster than light in order to deliver his gifts around the world? So if we could show that Santa Claus had to move faster than light, then that would show that Santa Claus can't be real, right? So we're going to see how fast Santa Claus actually needs to move. So I said this is going to be a mathematics-free discussion or talk, but there is a tiny bit of mathematics. There's this one simple fraction here. Speed is really just distance divided by time, right? And so let's first consider distance. How far does Santa Claus actually need to move in order to deliver all the gifts to the children around the world? Well, to understand that question, we need to look at the world population. So the world population here is shown over the past, or over 100 years. course, like right now, we're right around here, and a little more than 7 billion people. I was born in 1963 when the population of the world was less than half of what it is right now. But of course, the problem isn't that Santa Claus has to deliver gifts to everybody in the world. He just needs to deliver the gifts to the children. And there's, about 1/3 of the population of the planet is under 18. So let's just say that people under 18 are children, so they deliver them. Santa Claus needs to deliver the gifts to only about 1/3 of the population of the planet. But it's even easier than that, right? Because Santa Claus only needs to deliver gifts to the good children in the world, right? So there's, not all children are good. So, it's an easier problem for Santa Claus, right? Now, I was born in 1963, where, just my quick estimate based on the children in my neighborhood, I'd say about 80% of children were good. But we all know that children are not as good anymore as they used to be. So the problem's actually gotten easier for Santa Claus as a function of time, because the fraction of children that are good has been decreasing. But since the population of the planet is increasing, the number of good children has been increasing and is currently probably, by my estimate, somewhere around 1.5 billion. So how does he visit all the good children in the world? This is actually a really complicated problem. It's known as the traveling salesperson problem. And I'd like to spend a little bit of time trying to work this up, because it plays into how far Santa Claus actually needs to travel. So imagine you've got a bunch of cities represented by these little stars here, and a salesperson has to travel to each of the cities to make a delivery or sell something. And the salesperson could just go randomly between the different cities, and they could imagine that'd be very efficient. They would be wasting a lot of time. They'd be wasting a lot of money. It would be very inefficient to just travel haphazardly between these different cities. So the salesperson, in order to maximize their profits and minimize their time, would want the most efficient route possible. This diagram here actually represents the most efficient route through those 60 different cities, right? So this is the most efficient way to do it. There is no other way to travel between these cities more efficiently than this particular route, right? That's the traveling salesperson problem. Now, this problem can actually be solved for small numbers of cities, right? It's actually possible to solve completely and accurately, without a doubt, for small numbers of cities. But when you increase the number of cities, you can imagine that the number of possible routes becomes much larger. And if you've got a tour where you've got to visit 3,038 cities, right? The number of possible routes is this, right? This is the number of possible routes between 3,038 cities. And oh no, I just realized this number here should have been an 8. I'm really sorry about that. So the problem gets much more complicated as you add cities, right? This is a map that's kind of, pixelated, but this is a map that was used in the computation of a world tour for Santa Claus of more than 1.9 million cities worldwide, right? So they actually use the GPS latitude and longitude of even small towns, a very small number of people around the world. And there's, more than 1.9 million of them. And this was actually run through a computer, which basically shows that, you need a massive computer to solve this problem. This basically shows that Santa Claus, it's probably the reason that Santa Claus is at the North Pole, right? Is because you need massive cooling power to cool down a supercomputer like this, right? So basically Santa Claus's air conditioning bills are not very big at all. Of course, then again, maybe he's contributing to global warming up in the North Pole. But anyhow, so he's solved this problem, and he's actually found out that the most efficient route to travel between those 1.9 million cities is a little more than 7.5 million kilometers. Okay, so this is the actual route shown here on this map, and you can see that thankfully Hawaii is right up here. You can see he visits all the islands and all the different towns in the islands, right? So this is the most efficient route to visit 7.5 million, over 1.9 million cities around the world. It takes 7.5 million kilometers to do it. So how far does Santa actually travel? Because the problem the problem of moving between the cities isn't the only problem, right? Like once he's actually in a city or in a town, he has to go between each of the different homes, right? And that actually turns out to be a much bigger problem, a much larger distance than the distance between the cities, right? And we're not going to be able to calculate this exactly for every single house, but we can make approximations based on the population density of the world. So we know that there are about 7 billion people in the world, now about 7.5 billion people or so. And we know that that means that, if you assume that there's roughly 5 people per household, that there's about 1.4 billion households. And if we do the math, that means, or if we assume that there's about 1,000 people per square kilometer within the cities. So that's within the cities, we think that there's about 1,000 people per square kilometer, which is kind of like a normal city. That sort of means that on average, there's about 70 meters between households. And so if you do the math there, and I won't bore you with that, it turns out that the distance between homes within cities is about 100 million kilometers. Okay, so how far does Santa have to travel in total? Well, he's got to travel 7.5 million kilometers between the cities, right? That was the traveling salesperson problem. And he's got to travel about 100 million kilometers within cities to get from house to house, right? So the total annual distance that Santa Claus needs to travel is about 108 million kilometers, okay? Now, to give you an idea of what that's the scale of that distance, right? The distance between the Earth and the sun is about 160 million kilometers. So Santa Claus needing to travel 108 million kilometers every year is about 2/3 the distance to the sun, right? That's a long way for Santa Claus to travel. Now, we've only talked about the numerator in this equation, right, to calculate the speed. If we want to know the actual speed, we also need to know how much time Santa Claus has. So we can think about this very interesting, right? So Santa Claus, has to travel. He has to travel in the dark. He has to travel while children are sleeping. Most people would say that Santa Claus has got 24 hours to deliver his gifts. But let's think about this a little bit more carefully, right? Let's look at a time zone map of the world. And let's say that Santa Claus starts on the western edge of the international date lag, okay? And he starts at 8 p.m. because all good children are in bed by 8 p.m. like I was when I was a child. So he started at 8 p.m. the evening of December 24th, delivering gifts. And then Santa Claus travels westward, and he can travel and continue traveling until it gets to be 6 p.m. on 6 a.m. on December 25th on the eastern edge of the international date line. And if you work that out, it turns out that that is 34 hours of travel, right? So Santa Claus has 34 hours to deliver the gifts, not just the 24 hours that you might think. So let's work out what his minimum speed has to be. 108 million kilometers in 34 hours. Turns out that's 3.2 million kilometers per hour. Well, that is nothing. That's not relativistic. That is just 0.3% the speed of light. And we use this letter C here to represent the speed of light. So 0.3% C means 0.3% of the speed of light, right? So that's nothing. Santa Claus does not need to move at relativistic speeds in order to deliver the gifts, okay? At least that's the first conclusion. But let's think about this a little more deeply, because Santa Claus got to do a lot of things, right? He's not just traveling, right? He has to travel from city to city. He has to get in between the homes in a city, so the intercity travel. He has to stop his sleigh. He has to enter the chimney. He has to deliver his gifts. He has to eat the milk and cookies. And we know he spent a lot of time eating milk and cookies because all of us have left the milk and cookies out, and he always eats the milk and cookies, right? So he always stops, and that's not fast, right? I mean, you got to have the cookies, you got to drink the milk to wet your mouth. So that takes a long time. And then he's got to exit the chimney, and he's got to start his sleigh back up again, right? So that is a complicated process. So, we have to allocate the time appropriately between all these different elements. So I assigned 25 seconds to travel from city to city, 335 seconds to travel within the city to the different homes. And that gives them a total of 360 seconds to travel 108 million kilometers. And he worked that out. That works out to 299,792 kilometers per second, or 99.999% of the speed of light. Okay. So I think that now answers the question, does Santa Claus need to move faster than the speed of light? And the answer is no. Therefore, Santa Claus is not breaking this rule of relativity, right? Test number 2. Test number 2, does Santa Claus have to travel faster than light in air? This might seem like a silly question, right? But it's actually pretty important. And I think it actually provides another test on whether or not Santa Claus exists. Conventional wisdom is that nothing can travel faster than the speed of light. That's what everybody says. Nothing can travel faster than the speed of light. But that's not actually the case. The relativistic wisdom is that information cannot be transmitted faster than the speed of light in a vacuum, okay? Now, when we say in a vacuum, we don't mean in your vacuum in your house, okay? that's not the kind of vacuum we're talking about. We're talking about a vacuum in outer space, right? In space, there's basically nothing in outer space, and so except for space. And so in space, when there's no other matter around, nothing to impede the motion of the light, the speed of light is exactly, by definition, 299,792,458 meters per second. Right? That is the exact speed of light in meters per second in a vacuum. But light can travel slower in other material. So imagine that we've got this diamond that's in outer space. Okay, so the diamond is in space, and so a light beam enters the diamond from the upper left, and because it's in outer space, it's moving at the speed of light. Then when it enters the diamond, it instantaneously slows down to a really lethargic 40% of the speed of light, or about 121,000 kilometers a second. And then as soon as it exits the diamond, it instantaneously accelerates to the speed of light again, right? So the point is that inside material, like diamonds or air or anything else, light actually slows down. Okay, so keep that in mind. Now we're going to move on to discussing atomic and subatomic particles, right? So let's examine the atom. And we've probably all heard about atoms. Atoms are extremely tiny. Atoms are often shown as like billiard ball-like things. I don't like that analogy for an atom. I look at more like a fuzzy electric ball, fuzzy ball, like a cotton ball or something like that. So an atom is very tiny. It's about 1/10 billionth of a meter in diameter, the typical atom. And again, I hate numbers like that. They're impossible to understand. But when we're talking about distances and speeds and sizes that are, so crazy by our, relative to what we know in our everyday lives, it's really difficult to explain it otherwise. But, let's try it. This is a hair that's been blown up, obviously in a magnifying glass. And you could fit 1 million atoms across one of your hairs. Okay, so atoms are tiny. And inside of an atom, the thing that actually gives us its puffy electric size is these things called electrons. Electrons have a negative charge, and electrons interact with photons. Photons are these waves that we talked about, waves of light, or you can think of them as packets of energy. Depends on what you're trying to explain. And so photons and electrons interact together because of the electron's negative charge. And at the very center of an atom, taking up a minuscule volume of the atom, is something called the nucleus, right? And the nucleus itself is composed of things called protons and neutrons. And the protons and neutrons themselves are contained of things called up and down quarks. And the quarks interact through something called gluons. Now, this may sound really complicated, but just keep in mind these 5 particles here, the photon, electron, gluon, up quark, and down quark, these 5 particles make up everything you've ever seen or touched or felt or smelled in your life. Right? 5 particles make up absolutely everything in the universe that you know about. Right? Those 5 particles. So these are particles, of course, are critical to nuclear fission, the nuclear reactors that we use to power our homes in some countries. And in nuclear fission, there's some very interesting process that happens. In a nuclear reactor, typical nuclear reactor has got a uranium nucleus. And in nuclear fission, what happens is the uranium nucleus is struck by a fast-moving neutron. And when the neutron strikes the uranium nucleus, it basically blasts it apart into 2 different lighter nuclei. And it also releases some other neutrons. And it also releases electrons, right? So there's the electrons that fire off. Now, this is important to this test because the electrons coming out of that reaction are moving at 99% of the speed of light, right? 99%. Those electrons that come out of the nuclear reactions in a nuclear reactor are moving at 99% of the speed of light, which would be no problem if it was taking place in a vacuum, right? Anything can move at 99% of the speed of light in a vacuum. But the problem is that nuclear reactions inside of a nuclear reactor take place underwater, right? So there's water surrounding the entire uranium fuel in a nuclear reactor. And when the electrons get emitted, they are moving at 99% the speed of light in a vacuum, but they're moving through water. And the speed of light in water is only 75% of the speed of light in a vacuum, which means that the electrons are moving faster than light in water. Right? So things can move faster than light in a material, right? So the electrons move faster than light in water. And that is kind of an unnatural situation. And so the electrons try to slow down by emitting radiation. And that radiation, the Germans call it Bremsstrahlung radiation, meaning braking radiation, which is kind of a nice word. And we call it Cerenkov radiation. So Cerenkov radiation is the light that is emitted by these electrons that are moving faster than light in water. Now, you may think I'm just making things up and there's no way to show this, but in fact, here is a real picture of the inside of a nuclear reactor. This is the inside of a nuclear reactor. There's no light being shined on inside here. There's no blue light. There's no computer animation, computer effects going on here. This is the real light coming off of a nuclear reactor. And it's due to the Cerenkov radiation coming off of the electrons that are moving faster than light in water, right? I think this is just incredible, right? That there's this blue light. So you're probably all wondering by this point, what does this have to do with Santa Claus, right? So Santa Claus, right, is a very high-tech Santa, right? So he knows what he's doing. The speed of light in air is about 99.97% of the speed of light. But we've already established that Santa Claus is moving at 99.999% of the speed of light, right? So Santa Claus is moving faster than light in air, right? So test number 2 was, does Santa travel faster than light in the air? And the question is yes. And so you might think that this is a problem, but I actually see this as a strong evidence for Santa Claus, because I defy you to find an image of Santa Claus that doesn't show him surrounded by this ethereal blue light, right? I think this is clear evidence that he's emitting Cherenkov radiation and that he is moving faster than light in air, but this is evidence that he's actually doing it correctly and he's obeying the laws of physics and relativity. Finally, test number 3. Are observations of Santa consistent with relativistic time dilation? Well, first of all, I got to explain time dilation to you, right? So time dilation is often explained in terms of this thing they call the twin paradox, and there's actually no paradox about it at all, okay? It's just called the twin paradox. You could call it the twin phenomenon would be a much better way to do it. And it's often illustrated with two identical twins. In this particular case, they're identical physically, but psychologically, they're quite different. The twin at the top is a very adventurous child and decides that he's going to take a trip on a spaceship that goes to another star system, another planet that is 27 light years away, 27 light years, okay? And this spaceship is amazing. It's going to be able to move at 99.9999% speed light. It's basically the same speed as Santa Claus. And that spaceship is going to travel. And due to the effects of relativity, on that spaceship, time appears to move very slowly, right? So for that child going to that distant star system, time moves very, very slowly. You could just see the clock tick over there, right? So the spaceship goes for 27 years to the distant planet. It does some studies there, comes back for 27 years. So 54 years have gone by. And after 54 years, the child hasn't aged at all. The child's been gone for 54 years and hasn't aged. Okay? The other child is very cautious, very careful, unwilling to take risks. And that child decides to stay back on Earth. And on Earth, time passes as normal, right? Just like we're experiencing it right now. So after 54 years, that child becomes a 58-year-old professor at the University of Hawaii, right? So this is the twin paradox. Very fast motion slows down time, right? Now, let's go back to our particles. This is a complete list, a complete table of all the particles that are in what we call the standard model of particle physics nowadays, right? Don't have to pay too much attention to all of them. We've already talked about these 5, the electron, up and down quark, and the photon and the gluon. Forget about those for now. Now we're going to talk about this particle called the muon. The muon is a very interesting particle, but like I said, the other particles are the ones that, affect everything you do every day. Muons are extremely unstable particles. If you take an individual muon, if you could somehow control a muon, put it in space in front of you, right? It would spontaneously decay, just for no reason at all. It just decays into 3 other particles, an electron and 2 neutrinos. Doesn't matter too much to the story of what it actually decays into. The thing is that spontaneous decay takes place after just 2 millionths of a second. So that means you take a muon, you put it in space, it'll just spontaneously decay into these other particles after 2 millionths of a second. So even if that muon was traveling at the speed of light, it should only be able to travel half a mile, right? Before it decays, right? So if you could take somehow a muon and you had it traveling at the speed of light, it would only last half a mile before it spontaneously decayed. So now we can talk about these things called cosmic ray showers. Cosmic ray showers are due to particles that come from space. So our outer space is filled with all these charged particles that are produced in stars and supernova and the galaxies. It doesn't matter too much our story right now where they come from, but they're slamming into our atmosphere constantly. When they slam into our atmosphere, they have very high energies and they interact with other atoms and molecules in our atmosphere. And when they interact with the other atoms in our atmosphere, they create other particles. Particles create other particles. And those particles in turn have high energy and they interact with other particles in our atmosphere. And this process continues on until eventually it gets down to the surface of the Earth, where your body is constantly being bombarded by the products of these cosmic ray showers, right? Again, I'm not too worried about that radiation. The point of this story is that many of these particles are muons. And we know that muons can only travel half a mile. So the question is, if they can only travel half a mile, how do they make it to 15 miles down to the surface of the Earth? And the solution is that is due to relativity. These muons are moving at nearly the speed of light. And at nearly the speed of light, time slows down for them. So even though they think they're spontaneously decaying after 2 millionths of a second, because of relativity, to us, it looks like they're living a lot longer. And that's how they actually make it down to the surface of the Earth. So time dilation is real. It actually is a real effect and we can measure it. We know what happens. And that seems like a very esoteric example, which many of you don't know about, but this should bring it home to you. GPS satellites, which we rely on every day. All of us use it now to get, to the grocery store, right? Even though we know exactly where the grocery store is, we still use our GPS to get to, our Google Maps, right? To get to the grocery store. These GPS satellites are at an altitude of about 20,000 kilometers above the surface of the Earth. Well, 20,000 kilometers above the surface of the Earth, gravity is weaker than it is on the surface. And the fact that the gravity is weaker up there means that clocks tick faster. Time actually passes faster on those satellites than it does on the surface of the Earth. It passes faster by about 46 microseconds per day, 46 millionths of a second per day. On the other hand, these GPS satellites are traveling at 13,800 kilometers per hour. Now that's very, very slow compared to the speed of light. But even so, it produces a measurable effect of about 7 microseconds per day, 7 millionths of a second per day. And it speeds the clocks up, slows the clocks down by 7 microseconds per day. So gravity is causing them to speed up by 46 microseconds, and their speed is causing them to slow down by 7 microseconds, so that the combined discrepancy is about 38 millionths of a second per day. Now that might sound like nothing at all, right? But 38 millionths of a second a day is absolutely critical. When they design these satellites on the Earth, they set their clock to tick slower than clocks on Earth, so that when they are launched into their orbits, they are actually ticking at the correct speed relative to Earth, right? If they did not do this, if they let the clocks on those GPS satellites tick at the same way, at the same rate the clocks on Earth do, we would not be able to use our GPS. We would not be able to use Google Maps. So Google Maps relies critically on the two theories of relativity, special and general relativity, being right, and that we have a complete understanding of how they work, right? So we know that relativity works, and we know that time dilation, both from the general theory of relativity and the special theory of relativity, are correct. So what about Santa Claus? Santa Claus, as we've just discovered, moves at 99.9999% of the speed of light. Okay, how does this affect Santa Claus? Well, here's my evidence. This is Santa Claus circa 1930, 1943, 1954, 1961, 2005, right? The guy is not aging, okay? Time is clearly moving very slowly for him, right? He's not aging. And in fact, there's this picture of him from 10,000 BC, which shows him as very young. So over 12,000 years, he's barely aged at all, right? So test number 3, are observations of Santa consistent with relativistic time dilation? The answer is yes, Santa doesn't age, except very, very slowly. So in our hypothesis testing summary, is Santa's speed consistent with relativity? Absolutely yes. Is Santa's faster than light in air speed consistent with observations? Yes, he emits Cherenkov radiation. Are observations of Santa consistent with relativistic time dilation? Yes, he does not age. So in our tests of whether or not Santa is guilty of breaking the laws of relativity, we find him not guilty. There is no evidence that Santa Claus is not real. Mele Kalikimake, everybody.
Thank you so much, Rob. That was great and very, very timely, very seasonal for us all. We are happy to take questions. So if anyone would like to ask Rob a question, feel free to either unmute your microphone, you can ask it directly, or you can enter something in the chat box. While we're just waiting for that first question, I just wanted to ask you where you got the idea for this presentation, if you've given it to other audiences. What sort of groups of people have you spoken to already on this topic?
I've been given this talk for 25 years, I think. Unfortunately, I can only pull it up between about Thanksgiving and Christmas. And I got the idea when I was working at Fermilab, which is a particle accelerator outside of Chicago. And they had a Christmas newsletter, which sort of presented this idea in sort of like a half-page or one-page article. And I thought it would make a really interesting, full-length talk, just a, humorous little talk.
There's a question in the chat. Should we be concerned about Santa's effect on global warming, given all this zooming around he's doing every year?
Yeah, well, yeah, of course, it would take a lot of energy to power Santa Claus's sleigh. And that would be a major contributor to global warming. I'll actually have to work that out. Maybe Santa Claus is causing global warming. And then, of course, there is the fact that he needs to use the supercomputer to calculate its trajectory. And as the population increases, or his path, and as the population increases and new cities occur, and population moves around, he's got to change his path all the time, right? So that takes that supercomputing power, which could be contributing to melting the North Pole.
Absolutely. Does anyone have any questions that they want to just unmute and ask?
Will this presentation be available for sharing? I'd love to share this with our kids or grandkids.
Yes, indeed, Andrea, we are going to make this available. So we have been recording and posting all the presentations so far through this webinar series on our CNS YouTube channel. And there are links to each of these in the invites that go out each month. So you can find it that way, and I'll hunt it down, see if I can put it in the chat as well. But we will be posting this presentation, usually have them up within about 24 hours of having them given. So lots of time to share them with the rest of your family. Okay, other questions coming in the chat. Tell me again why gravity is higher on a GPS satellite than on Earth.
I'm sorry, could you repeat the question?
There's a question here. Why is gravity higher on a GPS satellite than on Earth?
Sorry, the gravity is less strong. So gravity is stronger on the surface of the Earth than it is at the 20,000 kilometer altitude of the GPS satellites, right? So gravity is less. And but gravity slows down time, right? So right now on the surface of the Earth, gravity time is moving slower than time moves at the altitude of the GPS satellites, right? So time is moving faster where the satellites are.
Very good. Thank you, Rob. And I think there's a suggestion in here about Santa's capabilities for mining asteroids.
So that's certainly a reference to one of my fields of research that I do, that I'm working with this company called Transastra Corporation that is trying to develop technologies for mining asteroids for water. And when we consider the trajectories to the asteroids in a lot of detail, I think that even then we don't need to be too concerned about relativistic effects because the travel times are short. So yeah, we're not moving anywhere near fast enough to be really too worried about relativity.
Very good. Thank you so much, Rob. This is really fabulous. Before we end, though, I want to take just a moment and introduce Sarah Lynn Smith from the University of Hawaii Foundation. She's a development officer who works with us at the College of Natural Sciences, and she wanted to share an important message with you all.
Thank you, Allison. I wanted to thank everyone for attending this wonderful lecture. I had no idea that learning physics could be this much fun, Rob. Thank you. This was fabulous, and I'm sure that it will be searched repeatedly online. Somebody asked, by the way, I have found if you do a Google search with Pilina series, YouTube, all of the recorded series will pop up for you to find, and this is number 8, and we have more to come. I wanted to thank you all. Many of you are donors to the college and alumni of the college, both. And so thank you for attending and supporting the college. This being the end of the year, I wanted to also remind you that the college always needs support. And if you are inclined this holiday season or the end of this fiscal year to be wanting to be philanthropic in any way, we hope you'll remember the College of Natural Sciences. You can give online at uhfoundation.org. You can find an online giving space there. You can give with a credit card. If you are interested in exploring other ways of giving, such as planned gifts and estate planned gifts, or stock transfers and that sort of thing, please don't hesitate to give me a call. My contact information is on the invitation to the Pilina series. I am Sarah Lynn Smith at University of Hawaii Foundation.org, and I would be happy to help you and talk to you and answer any questions you may have. But again, just thank you for coming. This is a new series that we started this year, and we're very excited about it and so delighted that so many have been attending. Thank you.
Thanks, Sarah Lynn. I want to say a final thank you to Rob. That was really a fabulous talk. And just looking at all the comments coming in through the chat, I can tell that the audience really enjoyed it. It's really fabulous that you're able to share this lighthearted perspective on physics and astronomy, linking it in with our season right now. So thank you for that. I think we'll have a lot of people viewing this recorded lecture on our YouTube channel.
Thank you.
And yeah, absolutely. Thank you again. Aloha. Thank you everyone for coming. Just a quick heads up on our next seminar. I want to let you know about it. We're looking forward to seeing you all soon in the new year when it comes around. Our next webinar is going to be held on Wednesday, January 26th at 2 p.m. and it's going to feature Dr. Monique Chiba, who's a professor in our Department of Mathematics here in the College of Natural Sciences. Dr. Chiba has been working hard on modeling the COVID pandemic. And so she's going to be sharing some of her research with us on modeling disease outbreaks and what we can learn from these sorts of experiences. So thanks again to all of you for attending. I hope you all have a wonderful holiday season and take care. We'll see you again in the new year. Aloha.